ndapongolere kuku bonganda kumeme bonganda kutate bonganda kusezi ndapongolere meme ondalimbirwa kuku meme ondapongolere kuku tate ondalimbirwa sezi bonganda kumeme bonganda kukuku bonganda kutate ondapongolere sezi
Good afternoon. Bill Sverdlik here, ready to entertain you some more. Today's discussion is on clustering, and I just need a moment here to untangle a web of wires on my desktop here. At this point, you should have already read the two short PDFs, which were actually just part of a chapter out of a book by Margaret Dunham on data mining, where she talks about clustering. She gets into a lot more detail than we're going to need to get into. And I think that some of the issues that she raised in her book, in her chapter there, are worth going into some details because it might not be clear what she's talking about. But something that she started off the book talking about, or this section talking about, is she talked about clustering versus classification. And it's just worth mentioning that. And classification is very interesting, and in fact, it's a topic that we are going to talk about in this class. And it is true that both of these concepts have the idea that you have some member from your population, X, and you want to put X, you want to aggregate it into something. So there is some notion of aggregation here. The difference is that when we're talking about classification, the aggregates are labeled. They have names. Which is another way of saying they have names. When you're clustering, we're putting X in with a whole bunch of other things that we think are similar, but there's not necessarily a name associated with them. In other words, if this is some cluster D, I'm just giving it a name, then we're saying that the similarity between X and Y, where Y is an element of D, is high. They're very similar. Okay? But we don't necessarily give this a name like male or college students or dogs or whatever. We may do that, and we're going to find that actually it is a problem to give clusters names. We're going to talk about that later on. But all we're doing is we're aggregating elements by some similarity measure. And in the last couple of videos, we've indicated that so far when we're talking about documents recognized as vectors, we have, well, if they're recognized as vectors, we have two different ways of measuring similarities. We had yet a third way, the Jaccard coefficient, which really didn't have anything to do with recognizing the documents as vectors. But anyway, so that's where we're going in this particular chapter. Now, again, in the book, she goes into a very, very detailed, there's a drawing in there where she says there are lots of different clustering algorithms, and my goodness, Margaret is correct. And she gives this really, really broad diagram over here, and she talks about, well, we've got hierarchical, and then we have these things called partitional, She got over here, there's something called categorical. She had a couple other ones over here. Then over here, she had something that was called agglomerative. And you should notice this agglam. It's the same name that I'm using for my things up here. So obviously we're going to be talking about these things. There is something called divisive. And basically she says agglomerative or bottom up, where she says divisive or top down. There is this thing partitional. So we're not going to be talking about all these different things in here. In fact, we are just going to be considering two different clustering algorithms. So one of the ones we're going to be doing is in fact called agglomerative. And then the other one we're going to be doing is sometimes referred to, it's either sometimes referred to as k-means. Sometimes it's called KNN, which means K nearest neighbor. And the difference between these are in fact the following. When we're talking about agglomerative and it's bottom up, we're going to have all of our individual elements down here. And then what's going to happen is we're going to decide, well, who's the closest one to this one? And maybe it's this one. So we form a cluster. And then this one over here, maybe the closest one is that one there. And then maybe these two are very close. And then maybe these two over here are very close. So now what we would do is we would come over here and say, well, that's very close to this one. And it looks like that. And what we keep doing is whereas down at the bottom level, there were just single elements. In other words, each cluster only had one element in it. When we get way up to the top, there is only one cluster, and it contains all of the elements in it. So that is basically what the talk on this video is all about. And let's get right down to it. So what I want to do is I want to talk about agglomerative clustering. This is an algorithm. Agglomerative. And again, some of you may, the word glom, I don't know if there's a Latin or a Greek root to that, but basically kind of means stick or glue. At least that's how I think of it. I've seen that word in other places. And the example that your author gives here says consider a graph, a connected graph of 5 cities. Giving intercity distance. So we can imagine that I've got A, B, C, D, and E. And there are roadways connecting all of these different cities. So this is, in fact, a complete graph. Do you all remember that word from your discrete math class? So I think they're all connected here now. Is that right? No, A is not connected over here to C. Now I think I've connected them all. And let us suppose that the distances are like this. From A to B is 1. From A to C is 2. Let's see. A to D is 2. A to E is 3. B to C is 2. B to D is 2. Um, no, B, I'm sorry, I've made a mistake already. B to D is 4. That's a mistake there. That should be 4. From B to E is 3. And don't worry, I'm going to draw a table that's going to make this a whole lot clearer. C to A is 2, C to B. C to D is 1. Let's see, E to D is 3. This is already a mess, so what I'm going to do instead is I'm going to come over here and I'm going to draw a table that looks like this. That's going to make things much clearer. And what it looks like is the following. So there's a 0 here, 1, 2, 2, 3. And then at B, I come down here and it is 1, 0, 2, 4, 3. 2, 2, 0, 1, 5, 2, 4, 1, 0, 3. Okay, so this matrix actually corresponds to the intercity distance here. I apologize for the mess here. I hope this is a lot clearer. A couple of things you'll notice about this matrix. First of all, it is symmetric, meaning that the distance from any one city to the other, A to B, is the same distance as B to A. So in fact, it is symmetric right down the main diagonal here. And of course, the distance from any city to itself is 0. And what my goal here is to go ahead and create a cluster here, or to cluster this whole thing. And let's see if I can do this and keep lots of things up on the screen here. Now, a couple of things I want you to notice here. Notice over here, it looks like the distance from between A and B is 1. And it also looks like the distance between C and D is 1. So what I'm going to do over here is I'm going to create something called a dendrogram. Which is a very useful thing to have. And the first thing I note in my dendrogram, if I start over here, and I call this 0, and I call this, I'll come over here and I'll call that 1, and that's 2, 3, 4, 5. I notice a couple of things. I notice that A and B are 1 apart from each other. So I'm going to come over here, and I'm going to call that A, and I'm going to call that B, and I'm going to cluster them, I'm going to put them together. Okay, they're 1 apart. And then likewise, I notice over here that C and D are each 1 apart. So I'm going to come over here, and here is C, and here is D, and they are also 1 apart. Now what I'm going to do here is I'm going to redraw this table. And what I'm going to do is I'm going to say over here, well now I've got AB, and I've got CD, and I've got E, and over here I've got AB, and I've got CD, and I've got E. Because now what's going on is now we no longer speak about how far is it from one point to another. We've got, by the way, we've got this point E that's just sitting out here. And two of the three sets that we're considering are already clusters. So what we have to talk about is what do we mean when we say how far away one cluster is from another? And then the other thing we have to talk about is what do we mean when we talk about how far is a point from a cluster? And this is a discussion that is given in the book, and she refers to it as linkage. And there are several different kinds of linkage. There is something called single linkage. There is something called complete linkage. And there's something called average linkage. And this one over here we don't care about. These two over here we do care about very much. And what I'm going to be doing over here is I am going to be looking at the first example we're going to look at is going to be single linkage. And basically what single linkage means is if I have a cluster over here and I have a cluster over here, and maybe inside this cluster, here are 2 points, and over here are 2 points. The question is what is the distance between these two clusters? Well, what single linkage does is it says consider all of the distances and pick the minimum value. So in fact, in this particular one right over here, the single linkage would in fact be this bottom link, this one right from here to here. So that again, if I'm doing the single linkage over here in this one, we have to come over here and we have to say, okay, let's go back to our original one. And now what I'm doing, by the way, is I'm considering AB as a cluster, and I'm considering CD as a cluster. So the question is how far, what is the shortest distance from any point in AB to any point in CD? And I think we can see over here that, well, it's either 2, 2, 2, or 4. So the minimum of that would be 2. So the distance between AB and CD is 2. So again, this is going to be on the diagonal. So I come over here, and this is going to be 2, and this is also 2. So now the question is how far is it from AB to E? Well, I take a look over here, and I see that either one of AB to E is 3. And now I go, how far is it from CD to E? And I notice over here there's a 3 and a 5. Well, I'm going to pick the minimum one. So the minimum one there would be 3. And it looks like that. And now what I'm going to do is I'm going to come over here, and when I go ahead and do my dendrogram, I'm going to come over here and pick the smallest number and put them together. So now it says I want to cluster AB with CD, and that's going to be at 2. So I come over here, and I do that. And now if I wanted to, I would come over here and make one more table, and the table would have A, B, C, D, and E, and it would have A, B, C, D, and E, and we know that there would be zeros there. And the question is how far is it from A, B, C, D to E? And I think we can see that the answer to that is 3. So we would come over here, and we would do that. And what this dendrogram has done is this now provides a clustering of the original set, assuming this thing called single linkage. Okay, so here it is. And notice one of the things that we can do is we can come over at any point and we draw a horizontal line. And what happens is if I draw, for example, if I draw a horizontal line here, I come back and I just get one cluster that has A, B, C, D, and E in it. If I come over here between 2 and 3 and I draw a line, you can see that I have 2 clusters. And one cluster is A, B, C, D, and the other cluster would be E. If I came down here and drew a line, okay, you can see that what I'm doing is I'm breaking it down until finally I get to the point where I just have the individuals. If I were to draw a line between 0 and 1, you could see that I'd have 5 different clusters. Okay? On the other hand, if I were to draw it between 1 and 2, I would have 3 clusters. So this idea of drawing this horizontal line and breaking up the dendrogram is also another issue that we're going to consider in a paper that you're going to read. So that is single linkage. What I want to do now is consider the other one, which is called complete linkage. And I want to go back to the original drawing here. Okay? And again, I'm going to come over here and I am going to draw. So first of all, what I'm going to do here, again, I will notice that at least initially it looks like A and B are going to be right near each other. So here's A and here's B. And again, if I come over here, we can see that C and D are also right near each other. I'm going to come over here and I'm going to put C and I'm going to put D. And then the other thing I'm going to do, and this may seem a little bit strange right now, I'm going to come right here in the middle and put E, and you'll see why in a moment. Now, it is true, if this is at 0 and I come up here to 1, these are still like that. Okay? And that means that, again, what I could do if I wanted to is I could redraw a table, and I'd have AB, and I would have CD, and I would have E, and over here I'd have AB, and I'd have CD, and I'd have E, and there's going to be zeros down the diagonal. But now the question is I ask, how far is it from AB to CD? Well, remember what's going on in here. So I've got, here's A and B, so I'm going to come in over here, and here's A, and here's B, and here's CD, and let's call this C, and let's call that D. So from A to C is 2. From A to D is 2. From B to C is 2. And from B to D is 4. So remember, what we do now for complete linkage is we would pick the biggest one of these numbers. So I am going to say the distance between AB and CD is now 4. Okay? And now the question is how far is it from AB to E? Well, from AB to E, it looks like it's 3. And how far is it from CD to E? And we can see that it's either a 3 or 5. Well, the bigger number is 5. So now, when I come back over here, and I want to know what's the next step in building my dendrogram, I come over here and I look for the smallest positive integer. And the smallest positive integer is 3. And that's connecting E and AB. So I come over here to 2, and I come over here to 3, and that's why I put E in the middle here. And I'm going to go, this gets clustered like this. And now, if you want, I would come over here and I would draw ABE and CD. And I'd come over here and I'd go ABE and CD. And of course, there are zeros on the diagonal. And the question is how far is it from ABE to CD? And you could come over here and you'd go ABE to CD, or you'd come over here and you'd go AB and E to CD. Well, it looks like the biggest number I see is a 5. So that means I'm going to go 4, 5. And I would draw this. So remember, this is with complete linkage. Okay, and you can see, let me see if I can find the other one. There it is right over here. It's a very different dendrogram. So here's the question. Why complete linkage? It seems very counterintuitive. Well, let me ask you a question. Suppose this is, suppose I had a cluster that looked like this. There's a cluster. Here's a cluster. And let's suppose up here is a cluster. Now what I'm going to do is I'm going to change colors of my pen. That's fine. All right. Yeah, red. Okay, so let's take a look at this for a second. So suppose I am doing a agglomerative clustering and I'm at these three here now, and the next step is to join two of these together. If I were doing single linkage, well, single linkage, take a look. These 2 points from here to here, they're really close together. And in fact, these 2 points are much closer together than any of these 3 points are to either this one or this one, which would say that if I were doing single linkage, I would now cluster these two together. Does everybody see that? And now what I'm going to say, let's change colors. Suppose I were to come over here and I were to do complete linkage. Ooh, that's a terrible color. Let's try this one. If I were to do complete linkage, it looks like that I would probably cluster these two together. Well, here's the question that I have for you. Suppose I did single linkage. Now, if I did single linkage, that would suggest that this point right over here and this point right over here are similar. And if our similarity is being based on distance, we can see that these guys really aren't that similar at all. Okay? Whereas if we were to take a look over here at this cluster over here using complete linkage, there seems to be much more similarity between all of the points in there. Okay? And in fact, it turns out that when you're doing textual clustering, it's hard to say that, textual clustering, one typically prefers complete linkage. And the reason is they say it has more cohesion. In other words, that if I were to look at this cluster of the complete linkage and think of each of these points as being textual documents, they are more alike to each other, okay, than this one would be alike to that one. And that certainly appears to be the case in this one. Okay, I hope that wasn't too bad, and I hope that everybody is comfortable with the different linkage ideas and with agglomerative clustering.